Okay, we're picking up where we left off in the previous video. We're going through this final section in the pre-algebra chapter, which is mainly on rational expressions, but we're also going to talk about some additional operations on radicals at the end of this video. Okay, so where we left off was we were about to talk about complex fractions and how to simplify complex fractions, also known as compound fractions. And so, okay, a complex fraction or a compound fraction, it's a very simple idea. All it is so we've got some ratio here. Here's a fraction bar, which we know that with a fraction bar you have a numerator and a denominator. Okay, if there's at least one fraction in either the numerator or the denominator, but this fraction could be, maybe there's a variable in the denominator, but or maybe there's not. Maybe you have like something like that, whatever. If you just have a fraction in the numerator or the denominator of a fraction, then this entire expression or term here, you call a complex fraction or a compound fraction. Okay, now this is a little bit confusing because, you know, it makes it, with the title of this section containing rational expressions, and we just spent the whole first portion of this section talking about rational expressions, it makes it seem like, okay, well, complex fractions must be some sort of some sort of a rational expression, or maybe the complex fraction can only contain rational expressions, and that's actually not the case. It's just it's kind of algebra is kind of a tough subject that way, in that there's just a lot of random topics all over the place. So no, a compound fraction has nothing to do, intimately to do with rational expressions. You can have any type of, like this would be if you did 1 over, okay, then 2x plus, this is a compound fraction, right? Contains a radical. Obviously, this isn't rational. This is a compound fraction. We haven't gotten to logarithms yet, but if we had, this is a compound fraction. I mean, even this is a compound fraction. Okay. Now, if we take a look here at this first example that they give, so x over 4 minus 4 over x, because what we're trying to do here in this section is just learn how to simplify complex fractions. That's it. Okay. Okay, so here's a compound fraction, and the examples that we're going to work in this section and in the upcoming video they're going to be complex fractions that strictly consist of like rational expressions. We're not going to be working with like radicals in fractions or anything like that. It's just going to be these rational expressions in the numerator and denominator. Okay, but the principles we're going to learn on how to simplify them, you can apply to any kind of complex fraction in the future. Okay, but what's kind of confusing about this is that, so if what kind of expression is this? What category would you put this in? Well, according to the precise definition of rational expression, the mathematically precise definition, it's a ratio of polynomials. Well, this is certainly not a ratio of polynomials, because this, if we write this in the exponent form, this would be right, and that's certainly not a ratio of polynomials. That's a ratio of I guess rational expressions. Okay, however, if we think about the informal definition that I gave for how to identify a rational expression, this actually would meet the requirements for that informal definition. The informal definition that I gave was that you go to every expression, so like we could be summing more terms, but you go to every expression, and if you find just one variable that's raised to a negative integer exponent, then you're going to call that rational. And so in that case, this would meet that requirement. So by the informal definition that I gave, would this be rational? Well, I would say no. I would say no. This is a special case where you wouldn't call this rational, a rational expression. What you would call this is this is a complex fraction, and in the numerator you have a rational expression, and in the denominator you also have a rational expression. That's what I would say this is. But if in the denominator you had just a polynomial or something, if you had 1/4 plus x squared, then you'd say, okay, this is a complex fraction where in the numerator you have a rational expression and in the denominator you have a polynomial. This is a special case where that informal definition doesn't work. Okay, so now with that, then how do we simplify complex fractions? And again, this doesn't just apply to if we've got these rational expressions. These methods will apply in general for any kind of complex fraction. Okay, well, they present two methods here. So here's the first method. This is the order of operations method, and what they call it the order of operations method because when it comes to order of operations, if you're dealing with a fraction, then what you do is you simplify the numerator as much as you can, you simplify the denominator as much as you can, then you simplify from there if possible, like you cancel terms, and then you can apply, quote unquote, apply the fraction bar. If you end up with something like this, then you can actually apply the fraction bar and get rid of the fraction bar. Or if you can't, if it's something to where you can't apply the fraction bar, then you just leave it like it is. Just simplify the numerator and denominator as much as you can. Okay, so that's going to be the approach. We're going to how do we simplify this as much as possible? Well, what we're going to do is we're going to add these. We just talked about in the previous video how to add rational or subtract rational expressions. So we're going to go ahead and do that, and we're going to go ahead and do that in the denominator, and then we'll simplify from there. That's going to be the approach. So, okay, let's see. We've got, if we multiply this by x over x and multiply this by 4 over 4, okay, and then we multiply this by x over x and this by 4 over 4, then what do we get? Then what's the result? So we got x squared minus 16 over 4x over, and then x plus 4 over 4x. Okay, so this comes out to be x squared minus 16 over 4x times 4x over x plus 4. Okay, we can factor, so these are going to cancel, and we can factor this in the numerator, and we're left with x minus 4. Okay, now, so that's fully simplified, but remember, we have to specify that, well, x can't be 0, and x can't be negative 4. If x is 0, you're dividing by 0. If x is negative 4, 1/4 minus 1/4 is 0, right? Because, again, all we were doing is just cleaning this up. We weren't like saying this is gone now. No, the simplification process was just about cleaning this up. That's it. But this is still the original expression, so you can't input x is equal to 0. You can't input x is equal to negative 4. So neither can you input that here. Okay. Now here's the second method. It says multiply by the least common denominator. So what we're going to do here is multiply the numerator and denominator of the complex fraction by the least common denominator of all of the fractions in the entire complex fraction. Then apply the distributive property and simplify the numerator and denominator, and then simplify from there. So yeah, we're going to, okay, let's do this d to the minus 2 minus c to the minus 2. That's going to be 1 over d squared Okay, so what they're saying here is that we're going to, if we multiply the numerator and the denominator by the same number, it's like you're multiplying by 1, right? 1 in the form of a number over a number. So you take the least common denominator of all of these combined. all of the fractions in the numerator and denominator combined. So we can see that's going to be, we want to multiply by c squared d squared over c squared d squared. Okay, and so what's going to happen is we'll get c squared d squared times 1 over d squared is going to be c squared. And then here we're going to get d squared. And then, okay, now down here we're going to get, let's see, it would be c squared d minus cd squared. Okay, so now we've eliminated the fractions. And so now we're just left with a normal rational expression. So we just simplify it like we did in the previous video. So how do we simplify a rational expression? You just factor. So let's see, this would be c plus d times c minus d, difference of squares. Here we have, let's see, we can take out a c and a d, I believe, and we're left with c minus d. Okay, so c plus d over c d. Okay, but you know, you have to look at the restrictions. So c can't be 0, d can't be 0, both c and d can't be the same, you know, things like that, right? If c is equal to d, then you're going to get the same, you're going to get that 0 in the denominator. So you have to consider all of that. Okay, let's see. We've got 2 over 1 plus h minus 2 over h. So we just multiply by 1 in the form of the least common denominator of all of the fractions, but there's only one fraction here. So just multiply by the denominator of that fraction. Okay, so we're going to get 2 minus 2 times 1 plus h over h times 1 plus h. So 2 minus 2 minus 2h over, let's just leave this factored for now. Okay, 2 minus 2 is 0, so minus 2h over 1 plus h, over h times 1 plus h. Okay, the h's cancel, so minus 2 over 1 plus h. There we go. But again, let's see, h can't be negative 1. Well, that's still the case here. H can't be 0. H could be 0 here, but no, you can't put 0 here. Okay. Now we're just like switching to a new, kind of a new unrelated topic in a way that's kind of not related to rational expressions. And we're coming back to radical expressions. So rationalizing the denominator of a rational expression. We already talked about this a couple of sections ago, but I think they want to expand on it a little bit. We're going to look at, like, what if we had, you know, yeah, there's a radical in the denominator, but it's a little bit different, right? It's not a single radical. So, okay. The same principle that applies to simplifying rational expressions also applies to simplifying algebraic fractions. For example, 5 over root x is an algebraic fraction, but not a rational expression because the denominator is not a polynomial. Okay, from section R.3, we outline the criteria for a radical expression to be simplified. So they restate the conditions here. Yeah, we talked about this when we on the section on radicals, simplifying radical expressions. So here's the two conditions that were associated with fractions, that you can't have a fraction appear in the radicand, so you can't have, and this is not simplified, and then you can't have a radical in the denominator of a fraction, and to consider that simplified. It's not wrong, but to consider it simplified, you can't have this. Okay, so in this example here, we use the property of equivalent fractions to remove a radical from the denominator of a fraction. This is called rationalizing the denominator. Yeah, so we looked at if we had this, right? We saw that when it came to the square root, you just multiply by 1 in the form of the square root over the square root, and you're going to get 5 root x over x, and you're done. Okay. Now, it was a little bit different if you had a non square root radical, like if you had the principal cube root of x, then no, you don't just multiply by the cube root of x or the cube root of x. That's not going to work. It only works out with the principal square root, because you have x to the 1/2, right? And if you multiply by x to the 1/2 over x to the 1/2, the 1/2 plus 1/2 is 1, so you get rid of the radical. You're trying to get rid of the radical. So if you had x, the principal cube root of x, okay, then really what you need to multiply by is x to the 2/3 over x to the 2/3, because then that's going to add to 1. Now, but you're wanting to add to the next whole number. So if you had, let's see, it would be maybe x cubed like that, right? How would you rationalize this? Well, this is equal to x to the, oh no, let me give another example. Let's switch this. This would be, okay, so yeah, here you've got x to the 1 over x to the 4/3. Well, you can't multiply by something that adds to 1, because 4/3 is greater than 1. So you need to do, let's see, 4/3 plus, let's see, would it be 2/3? Yeah, so you need to do x to the 2/3 like this. And then you'll get 2/3 plus 4/3 is 2, so you'll get x to the 2/3 over x squared. And you've still rationalized it now. So you've got, you say, so that was the idea of rationalizing if you have just a single radical in the denominator. Okay, but what we didn't look at was, what if you have something like this? So right, and you can think about this is not, these aren't variable radicals, but this same idea would apply. What if you had like a subtraction of or addition of radicals in the denominator? Well, okay, we can take advantage of the conjugate here. So if you multiply by the 1 in the form of the conjugate of the denominator, then what's going to happen? Well, we know the conjugate comes out to be a squared minus b squared. And so if we square these, we're going to, like, 7, the square root of 7 squared gets rid of the radical. So you're left with 7 minus 5 in the denominator. And then up here you've got, okay, so let's see, 4 root 7 plus divided by 7 minus 5 is 2. So 2 root 7 plus 2 root 5. There you go.